lesson 2.3b, estimating the derivative of a function at a point. A lot of the times they just kind of give you a table of selected values. So like for this particular situation, selected values of the continuous function h of t are shown. Very important to understand continuous. If it says that the function is continuous from 0, let's kind of graph something like this, and it's telling you it is continuous. So at time equal to 0, say t, and this is h. So at time equal to 0, it is 30 feet up in the air, something that's thrown up. So this is 30, at time equal to 0 is here. At time equal to 2, you got 0, 2, and you got say 5, you got 7, and you got something like 10 over here. So let's just say that something was thrown up in the air. So at time equal to 0 is up 30 meters up in the air. Time 2 equals, it'll be 40 feet up in the air. Let's just say here's 40. Just give you a rough sketch. 5 is 45, say here. 70, it just keeps going up. 7 seconds is 70, somewhere right here. 10 is up here. So it's just going up or something. But it's telling you it's continuous. See, it's just keep going, and there's no gap or nothing. It's just straight continuous. All right. So if it is continuous, we can just estimate what would be the rate of change at from 5 to 7. I'm just assuming that's what it's doing. I really don't know what it's doing. For all I know, okay. So that's what's going. What's the question? Let's see. What's the question? Well, the question here is to estimate the rate of change at time equal to 6. So where's t equal to 6? Well, t equal to 6 right here. There's 6. So what would be the rate of change here? See, going back to what we just always did from 1.1 is what is the slope here? What is the rate of change? Well, the best estimate we can do is to just get the two closest points given, that is around t equal to 6, no? Because t equal to 6 is here. Then you were given 2 points here. That's all you know. In reality, that's all you know. Maybe you could just put the point is here and the point is here, and these are the closest point. We don't know what these, we shouldn't care about those because these are the closest to what 6 is. And then we could just do a rate of change here. So we can go ahead and just get that answer by saying that h prime of 6 will be equal to 7 minus 5. That's going to be the inputs, and the outputs would be go back 70. The output of 7 is 70. The height, and the height at 5 is 45. So then you're going to just go 70 minus 45 is what, 25 divided by 2. So it's going to be 25 divided by 2 is about what, 12.5. And so it's going at about 12.5 what, meters per second. That would be the best answer you can get back to them if you're given that. Problem number 2, approximate the value of the rate of change at 4.5 using the data from the table. Well, you are given a graph as well, and by looking at the graph, they're not even telling you because they're assuming that you know that on this interval, say from A is 0 to B is 9, there is a jump discontinuity, saying that then we can there's a you can't find the rate of change exactly at 5, but there's a gap there. There's jump discontinuity. But even then, we don't care about that. We care about 4.5. 4.5 is here. 4.5. So now we got to get 2 points that are closest to 4.5 and do what we just did earlier. And now we're given a table here. Looking at the table, the candidates, definitely these are not candidates. The ones that are outside are not candidates. This is not a candidate. That's not a candidate. So these could be candidates. You are actually given the point 4.5 and where it's at. So at 4.5, it is at 3.193. And then at 4, you're given this one that is at 2.533. But these in between and including the endpoints, it is continuous. Why should you not use 5 and 1? Because at 5 it jumped down here, and if you do 5 and 4.5 here, it will give you this kind of approximation, which would be completely off. So the 2 points we're going to use are 4.5 and 4. So let's go ahead and do that. So the rate of change at 4.5 would be the f of 4.5 minus f of 4 over 4.5 minus 4. Use all the math, get a calculator, and that gives you the answer. Problem B. Is there a value of x for x greater than 0 less than 5 such that limit as x approaches 0? This is just telling you that is there anywhere where the derivative is equal to 0, where the slope is equal to 0? Where would be the slope equal to 0? Where you have a horizontal tangent line. So the only point here that I see that you can get a horizontal tangent line is there. This right here, it always has a constant positive slope, not there, and so x equal to 2 would be the only candidate to satisfy this. F prime of x is equal to 0 at a point where the tangent line to the graph of f has a slope of 0, and that would be where x is equal to 2. And that would be it for today. See you next time.